Good morning, everybody. It is 11 o'clock. Well, a few seconds shy of 11 o'clock. There we go. So we're starting chapter 9, which is on solutions. As you can see, there's no do now. We're just going to jump right into chapter 9. I'm going to say it now. There's only a few of you here, and I'm going to reiterate again, probably at the end of class. But just remember that if you need something from me, it's got to happen before 5 o'clock today, because I am going to be unavailable until next week. So no office hours this week. You don't have any assignments due for me this week. So you're kind of free and clear, but I would recommend working on chapter 9 stuff. So if there's no questions about kind of where class is going or anything like that, we can get started. But if you think of something, as always, let me know. Go for it. You don't have any assignments due this weekend. I'm not going to have you do assignments when I'm not available to help you. So your chapter 9 mastering chemistry assignments are not due until November 15th. Mm-hmm. Alrighty. So we're talking about solutions, and we're going to be talking about solutions again next week when we do a few select topics from chapter 11. So all of this will kind of tie together. So just to recap what a solution is, we've all kind of encountered solutions along the way, right? But a solution is a homogeneous mixture. So bring back the terms from chapter 3 when we were talking about mixtures and compounds and elements and all that stuff. So a solution is homogeneous. It's got two or more substances in it. If you look at a solution, you can't see, oh, there's the salt crystals and there's the water, right? So it's homogeneous. The solute, which is what's dissolved in the solvent, which we're going to talk about those words, they have to interact. And those interactions have to be great enough to where the individual particles of the solvent would rather interact with the solute than themselves. The solvent is present in a larger amount than the solute. So if you have a saltwater solution, you've got a small amount of salt, big amount of water. To talk a little bit more about solutes, they can actually be liquids, gases, or solids. So if you think about mixing two liquids together, or if you drink soda or other carbonated beverages, there's carbon dioxide in there. That's a solution, okay? A gas and a liquid. You can also have solid and a solid, like brass or steel, where there's a combination of metals that are melted together. So those are some examples of solutions and things that maybe you wouldn't think of as being mixed together and being solutes. With solutions, the solute cannot be separated by filtration. So you can't just pour it through a filter and then you separate the salt. But you can evaporate off the water and you'd be left with all the salt in a solution. And again, like I said before, you can't see the solute. You might be able to see a color change, like that copper 2 sulfate, but you can't see individual copper ions and sulfate ions in the solution. Unfortunately, we have to do a little bit of background to get some terms and things down, and then we'll start doing more practice along the way. So if you have a question, or if you need me to slow down, or if you just need me to stay on a slide for a minute so you can jot something down, just let me know. So we just covered solutions and solutes. Are we good on those two things? Okay. So let's do a quick learning check. Identify the solute in each of the following solutions. So remember, the solute is going to be what's present in the smaller amount. So A, you have 2 grams of sugar and 100 milliliters of water. Which one is the solute, the sugar or the water? Yeah, it's going to be the sugar. 2 grams of sugar is pretty small in comparison to 100 milliliters of water. For B, we've got 60 milliliters of ethyl alcohol and 30 milliliters of methyl alcohol. Which one is the solute? Yeah, the methyl alcohol. For C, we've got 55 milliliters of water and 1.5 grams of sodium chloride. And you can say A or B. We can do that. Make it a little bit easier on you. So the water is A, NaCl is B. Which one is the solute? Yeah, the salt is going to be the solute. And the last one, we have air, 200 milliliters of oxygen gas, we'll call that A, and 800 milliliters of nitrogen gas, which we'll call B. It's going to be A. All right, so that was just a quick learning check to make sure you have the idea down of solute versus solvent. It seems like most everybody's good on that one. Any questions? Alrighty. Now we have to talk about how solutions are formed. So you've probably heard, if you've taken chemistry in high school, like dissolves like. So when we were talking about the different types of compounds, we talked about polar compounds, nonpolar, ionic. Oh, that's okay. So how do we know that 55 milliliters is greater than 1.5 grams? So going back for just a second, if you think about the density of water is 1 gram per milliliter. So 55 milliliters of water should weigh around 55 grams. You can also think about just the sheer size of 55 milliliters versus 1.5 grams of salt. 1.5 grams is pretty small. I can tell you that a teaspoon of salt, if you were baking, a teaspoon of salt is somewhere in the ballpark of like 8-ish grams of salt. So 1.5 is really, really small. Does that help? You're welcome. Okay. So making solutions like salt water, like dissolves like, which means the solute and the solvent have to both be polar or nonpolar. Otherwise, a solution will not form. So if you have a polar solute and a nonpolar solvent, they're not going to mix well. Kind of like oil and water, they don't mix. Water is polar, oil is nonpolar. So does that concept make sense? If the solute is polar, the solvent has to be polar too. So let's do a quick learning check. We're going to determine whether each one of these will dissolve in water. So A, we have sodium sulfate. Will that dissolve in water? If you remember from chapter 6, this is an ionic compound, right? And it forms ions. Na plus, SO4 2 minus. Water, while it is a molecule, if you draw the Lewis structure, water is polar. So you've got a partial negative by the oxygen and a partial positive by the hydrogens. If you're forming positive and negative ions, you're absolutely going to dissolve in water, because those ions will be attracted to the partial positive and partial negative. Does that make sense to everybody? So what about the next one, gasoline? Is that going to dissolve in water? No. It's nonpolar, so it will not dissolve in water. And if you've ever filled up at the gas station during or right after a rainstorm, hopefully not during, because that kind of sucks, but there's usually, you can see kind of streaks in the water. Those streaks are gasoline and oil from people's cars and all sorts of stuff. It's just kind of floating on top. It will not dissolve in that water. Okay. Now we've got iodine gas. That's I2. This one, think about it a little bit. No, it's not going to dissolve in water. So it's a molecule with no charge. It is nonpolar. So just like the gasoline, it's nonpolar, so it doesn't want to be in something that is polar. So with these, you have to look at the compounds and figure out, is it polar, is it nonpolar, is it ionic? And that will help you. So that's a key that you want to remember. Polar and ionic compounds will dissolve in water. If it's not one of those things, then it's not going to dissolve in water. Does that help everybody? Now what about this last one, HCl? Will that dissolve in water? Yes. So we've got the hydrogen that will be attracted to the partial negative of the oxygen, and that chloride ion will be attracted to the partial positive of the hydrogen. So you may need to go back and kind of refresh yourself on chapter 6 to remember those classifications of polar and ionic and nonpolar. That will help you when you're trying to figure out whether a solute will dissolve in a particular solvent. Any questions here? Or are we ready to move on? So here's another one for you. When solid lithium chloride is added to water, it dissolves because, and we need to think about the lithium ions and the chloride ions. So I'll just give you a minute to read this and think it over, and then you can put your answers in the chat. I'll draw water again so you can visualize kind of the partial positive and partial negative. Alright, so for A, the lithium ions, they're positively charged. Opposites attract when it comes to charges. So if we have a positively charged ion, it's going to be attracted to the oxygen atom of the water, which has a partial negative. And for the chloride ions, they're negatively charged. So they will be attracted to the partial positive, which is the hydrogen of the water. Again, this is kind of mixing chapter 6 into our understanding of solutions. So we haven't talked about chapter 6 in a while, and you just had an exam on 7 and 8. So you definitely want to take the time to refresh yourself so this is a little bit more fluid, and because you have a final exam. But does this concept make sense? Now again, we're going to be moving at a little bit of a faster pace to get through the chapter, but always feel free to stop me for questions. We'll have hopefully a little bit of extra time next week because we don't have a full chapter to cover. So if there are some questions here, we can take a little bit of time to flesh them out and finish up chapter 9 next week. So always feel free to say, hey, Dr. Hefner, too fast. That's all right. So that's solutions. Just the basics. Solutes, solvents, how solutes dissolve in solvents, and what a solution really is. Now we're going to talk about electrolytes and non-electrolytes. So if you are interested in the medical field, you'll absolutely learn a lot about electrolytes. They're very, very important when it comes to maintaining what's called homeostasis. That's just kind of the regular normal state of the cell. And electrolytes are really important for organ function. So sodium, potassium, chloride, bicarbonate, all of these things are in your blood, they're in your cells, and you can test for these different levels because sometimes there are issues with sodium or potassium that can manifest themselves as cardiac problems. So these are really, it seems really small, but an imbalance can have a very big effect on your health. When it comes to electrolytes, we've got strong electrolytes and weak electrolytes. We'll talk about strong electrolytes first. Strong electrolytes completely dissociate in water, and they make ions. So when you think about strong electrolytes, think about ionic compounds. The classic one being salt, table salt. In these solutions, can actually conduct an electric current, okay, strong enough to actually light a light bulb. So we're talking about lots of charge in the water. When an electrolyte dissolves in water, you want to take note of what it looks like for the reaction. You're starting off with a solid like table salt. Then you have the yields arrow, and above it is water. So water is not a reactant here. We're just adding it to the reaction. All right. Once you add that water, you form sodium ions, which are aqueous, and remember that just means dissolved in water. And you form chloride ions, which are also aqueous. So know this kind of form factor for how a strong electrolyte dissociates. You're going to make ions. Let's say that I have potassium sulfate as a solid, and I dissolved it in water. What ions would I get? It's just like the sodium chloride, right? We're talking about potassium sulfate. So you're going to have potassium almost. So the SO4, remember that SO4 is a polyatomic ion. Oops. So if you have potassium sulfate, you're going to make potassium ions and sulfate ions. So I do strongly recommend that you revisit chapter 6, because you'll need to know your ions. You'll need to remember, the polyatomic ions and things of that nature. So go over that. I just wanted to give you another example to think about in terms of writing a dissociation equation. And we're going to get some more practice on that. We have some learning checks coming up. But just know, you're going to need to revisit those compounds. But does the idea make sense? If you have a strong electrolyte, you're going to produce positive and negative ions, and they're going to be aqueous, dissolved in water. Okay. As I said, we have strong electrolytes and weak electrolytes. Weak electrolytes only dissolve slightly in water. So you've got a few ions, but mostly undissociated molecules. A weak electrolyte, you can think of a weak acid. And this, I'll rewrite this because PowerPoint just keeps getting it wrong. So you notice here that we've got this kind of double arrow thing going on. That means that you're both dissociating and recombining to make the acid. So your acid is dissociating to make ions, and that's the forward direction. So let me do this. That's where your acid is breaking up into ions. And the blue is recombination. Those ions are finding each other in the water and reforming the acid. Does that concept make sense, that you have this equilibrium between the two? So just like before, you'll want to take note of the structure of this dissociation equation, okay? With a weak electrolyte, you're kind of going back and forth, and you have some equilibrium between ions and undissociated molecules. Now we get to non-electrolytes. So these things are absolutely soluble in water, but you're not forming ions. These are going to be polar molecules. The example that we have here is methanol. Methanol has a polar group on it. So that red and the kind of grayish white, that's an oxygen hydrogen bonded to a hydrogen. And that's polar. That allows the methanol to dissolve in water. But you're not producing any ions. And I'll rewrite this one again to you. You have liquid methanol, you add it to water, and it's just aqueous. Notice that the state of matter changes. So you've got liquid and then aqueous. If we had something like sugar, table sugar, that is a polar molecule. You're not going to form any kind of ions, so it would just go from a solid to, let's say you're making lemonade or something, you add it to water, now it's aqueous. So take note again of what that looks like. You're going from a liquid or a solid or something like that to simply being aqueous. Any questions about non-electrolytes? So let's do a quick learning check. Which of the following represents the dissociation of a strong electrolyte in water? A, B, C, or D? Now remember the strong, so I agree, it's C. So the strong electrolyte we're looking for an ionic compound dissolving in water. In A, what we're actually seeing is a chemical reaction. So this is taking ammonia gas, bubbling it through water, and you're forming ammonium hydroxide. So that's a chemical reaction. Okay. In B, we have methanol being added to water. So this one is actually an example of a non-electrolyte. And the same thing for D. Is that clear? And I know we're going fast, so if you haven't had a chance to watch the lecture and, it takes a little bit of time to marinate, that's okay. But even if you don't have answers, you can let me know, hey, I'm with you, Dr. Hefner. I'm following along. Because I like to hear from the people who are not answering to make sure that you're still with me. And thank you for your participation. It really does help. So let's do another one. This one's going to be writing the equations, which I know might be a little bit tougher. But I want to give you a couple of minutes to just try it or think about it. And then I will walk you through writing these equations. So you're going to write an equation for the formation of each of these solutions. You've got a strong electrolyte, a weak electrolyte, and a non-electrolyte. So that's A, B, and C. Look at your notes if you're taking notes, or kind of go back and look at the lecture notes that are already posted and try to piece it together and think about what it might look like. I'll give you 2 minutes. Oh, I appreciate you trying to write it in the chat. It's a bit difficult to write it in the chat. But you're almost there. So with the strong electrolyte, this is for A, you're going to form ions, right? So looking at the compound, we got to split it in two. We've got the potassium, and we've got chromate. Chromate is one of those polyatomic ions. So if we had a solid and we added our water, we would get 2 potassium ions, because remember that that subscript means that there's 2 potassiums here. So we're going to get 2 potassium ions, and we're going to get the chromate ion. So again, I strongly suggest that you review Chapter 6. It will help you with the strong electrolytes and some of the weak electrolytes too. No, I will give you those, just like I did on for the Chapter 6 exam. You will not need to memorize them. It helps if you recognize them, though, at the very least. Any questions on A? Go for it. So potassium is, it doesn't exist as a diatomic molecule. So remember what a diatomic molecule is. It's like hydrogen gas, oxygen gas, things like that. And from chapter 6, when we were writing out ionic compounds, there's 2 potassiums here to balance out the charge. The potassium ion is only 1 plus. The chromate ion is 2 minus. So you need 2 potassiums to balance out the chromate polyatomic ion. Does that help? You're welcome. Now let's do B. We have the partial dissociation of the weak electrolyte phosphoric acid in water. So partial dissociation means that we're only going to lose 1 hydrogen Now the other thing you need to remember here is that PO4 is a polyatomic ion that usually has a charge of 3 minus. So if that ion has a charge of 3 minus, if that has a charge of 3 minus, and we've got these hydrogens here that are each plus 1, then our charge for this is going to be overall negative. And that, again, will make more sense if you review chapter 6. But I at least want you to have a taste of writing these partial dissociations, because we're going to revisit them next week when we talk about acids and bases. Are there questions on this? I know that it may be like, I don't know that 100% get it, but does it sort of make sense to where if you felt like you reviewed it again, you might be able to write one of these? So we're only separating 1 hydrogen because it says partial dissociation. If it fully dissociated, it would be a strong electrolyte, but it's not. So this is something that you don't have the knowledge for, but when it comes to a weak acid like phosphoric acid, the more hydrogens you strip off, the more energy it takes to keep them in solution. So this acid likes to have it's more stable, it's happier, it takes less energy for it to stay together than for it to dissolve. It likes to hang out together. So when we're talking about solutes and solvents and how the interaction between the solvent and the solute has to be strong enough to overcome the solvent-solvent interactions and the solute-solute interactions. With these weak electrolytes, the interactions are not strong enough. So the electrolyte would prefer to kind of hang out together as a molecule than be broken apart. Yeah, if you have to take 105 after this, you might learn a little bit more about that. Good question, though. Okay. Let's do part C. We've got solid sugar dissolving in water. Sugar is absolutely a polar molecule, but it's not going to form any ions. So this is an example of a non-electrolyte. When you add it to water, you simply write the molecule with aqueous after it. So that's for a non-electrolyte. Any questions on any of these? This is going to be, you will have to recognize these things for multiple choice questions on your exam. So understanding how to do this learning check will be crucial. So make sure that if you don't fully understand it now, that you revisit it and try to work it through again and make sure it makes sense before you have the exam. Are we good on that? All right. So definitely go back through and rethink this one. Wouldn't be chemistry without some math. Not going to be as much math as the last exam. I know that was probably stressful for some of you. But you're not going to see that much math again. I promise. Just a little bit. We talked about electrolytes. And if you've ever been in the hospital or you've seen any, TV shows with, I don't know any of the new stuff out now, but like House or Grey's Anatomy, ER, that kind of stuff. You've seen somebody with an IV bag, right? Those have electrolyte solutions in them. And when we're talking about the amounts of electrolytes, what we're talking about is something called an equivalent. An equivalent is the amount of an electrolyte or ion that provides 1 mole of electrical charge. So it could be positive, it could be negative. In a solution, the charge of the positive ions is always going to be balanced by the charge of the negative ions. So if you have, let's say, a solution of sodium chloride, and you had 25 milliequivalents, which is usually what's used, of the sodium ion, you would also have 25 milliequivalents of the chloride ion. They have to balance each other out. And as I alluded to, with concentrations, we're usually talking about milliequivalents. That lowercase m is milli. And this kind of harkens back to chapter 2 when we were doing the conversions. So that's a prefix. 1 equivalent is equal to 1,000 milliequivalents. You'll need to know that one. It will not be provided on the exam. You'll just need to know that. So make sure you take that down in your notes. Put a star or something next to it if you print these off, or highlight it, because you'll need to know that. Now I want to show you how it works. And I did this example in the YouTube video, but I'm going to do it again here, and then we're going to do some practice together. The lab test for a patient indicates that their blood calcium level is 8.8 milliequivalents per liter. How many moles of calcium ion are in 0.5 liters of blood? We're going to start with part A. 8.8 milliequivalents per liter is a concentration. And if we know a concentration and a volume, we can get an amount. So the first thing that we have to do is go from milliequivalents per liter to milliequivalents. And the way that we do that is to multiply by volume. Once you have milliequivalents, then you can convert to equivalents. And that's using the equality that I told you need to know. So you write a conversion factor from that equality to get from milliequivalents to equivalents. To go from equivalents to moles, we have to write another conversion factor, which I'll abbreviate CF, to relate equivalents to moles. And I didn't explicitly talk about that in the last slide, so I'm going to show you what I mean in just a second here. So the first part is easy. Oops. Our volume is 0.50 liters. And we had 8.8 milliequivalents per liter. Now we need to write a conversion factor from the equality to go from milliequivalents to equivalents. That way, with milliequivalents on the bottom, we can cancel out the milliequivalents and be left with equivalents. For the third part, we need to talk about calcium. Calcium is a group 2A metal. Again, this is chapter 6, refresher, which means that when it forms an ion, the charge is 2+. One equivalent means 1 mole of charge. If I have 1 mole of calcium ions, that's actually equal to 2 equivalents. The charge tells you how many equivalents 1 mole is equal to. So if I had something that was 3+, it would be 3 equivalents. If I had chlorine, which is 1-, it would be 1 equivalent. I go over that in more detail in the YouTube video, so make sure that if you haven't checked that out yet, do it, because I don't go over every single nuanced detail during the live lecture. So writing that kind of an equality to know how many equivalents for a particular ion is something you'll need to be able to do. So we write a conversion factor from that equality to get us to the number of moles. Our liters cancel, and we're left with milliequivalents, just like in our plan. Then the milliequivalents cancel, and we're left with equivalents, just like in our plan. We cancel those out, and we're left with moles, and that's where we want to be. When you do that math, and you consider significant figures, you should get 0.0022 moles of calcium ions. So I'll give you a second. Look at it. Let me know if you have any burning questions right now. But I think the best thing to do would be to do a learning check where you can do a simpler problem and understand that. So this is all for part A. Part B is just asking how much chloride there has to be. And you have to understand, if there's 8.8 milliequivalents of calcium, then you have to have the same thing for the chloride ion to balance it out. So I'll give you a minute and let me know if you have questions or if you're ready to move on. But I'm literally going to give you a minute to just kind of sit on it and let me know thoughts, concerns, ready to move on and try something, anything like that. So talk to me. Questions? Do you want to try it? Let me know what's going on. Okay. Now let's try it. And that'll maybe help shake down some of the questions. So we'll do these one at a time together. Number 1, in 1 mole of iron 3 plus, there are how many equivalents? 1, 2, or 3? I agree. So there are 3 equivalents here. 1 equivalent is equal to 1 mole of electric charge. So your ion charge tells you how many equivalents you have. In 2.5 moles of sulfate ions, there are how many equivalents? So this is a mathy one a little bit. Take a minute and try that one out. Or if you worked ahead. Give myself some room here. So we're starting with 2.5 moles of sulfate ions. And we need to figure out what kind of a conversion factor to use for this. Well, we need to know how many equivalents there are in 1 mole of sulfate. We've got 2 equivalents here, right? So that's how you would solve that one. Figure out how many equivalents are in 1 mole. That's your equality. You write a conversion factor to take those moles of sulfate and convert to equivalents. Now let's do 3. An IV bottle contains sodium chloride. If the Na plus is 34 milliequivalents per liter, the chloride ion is no math needed for this one. The chloride ion should have the same concentration. They have to balance each other out. Questions on these? Yes, go ahead. Sort of, yeah. 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 So the ion charge is going to tell you the number of equivalents per mole. If it's 3 plus or 3 minus, then you have 3 equivalents per mole. You're welcome. Other questions? Or are we ready to move on? Okay. So what have we covered so far? We started with just talking about solutions in the basic sense. How they form, what's a solute, what's a solvent. Then we talked specifically about electrolytes and non-electrolytes, how they dissociate in water or how they don't dissociate in water in the case of non-electrolytes. And we talked about concentrations of electrolytes in solution and how to do some calculations. We can't talk about solutions without talking about solubility. So some things like salt or sugar have really high solubility. You can dissolve a lot of salt in water before you hit the amount of salt where if you keep adding salt, you're going to just see it kind of float to the bottom. If you know anyone who's older who may be affected by type 2 diabetes, if they're not taking care of themselves, they may end up with gout. So gout happens when you have concentrations of waste products in your blood that exceed the solubility in your blood. So you kind of have buildup of the solids in your blood, and that can cause swelling because those solids can get stuck in blood vessels. So solubility is very important, and understanding how to calculate solubility, but also just being aware of the fact that everything that you eat, you're eating chemicals. We don't like to think about it in that way, but you're feeding yourself chemicals, and those chemicals interact with each other and with your body. And the choices you make now will affect how your body lives later down the road. So don't forget that. I'm sorry, it's the mom in me. I'm sorry. But I want you guys to be great. Okay. What is solubility? It's the maximum amount of solute that dissolves in a specific amount of solvent. For the purposes of this class, most of the time the solvent is going to be water. This class is geared towards kind of folks who are interested in the health sciences. So water is not only a common solvent, but it's the biological solvent. It's the MVP. Solubility is affected by temperature. So we'll talk about how it's affected by temperature, but in general, if you warm up that water, you can dissolve more solute in it than if it were cold. Generally, we express solubility as grams of solute that can be dissolved in 100 grams of solvent, which again is usually water. When we're talking about solutions, we can talk about unsaturated versus saturated. An unsaturated solution has less than the maximum amount of solute. So you can still add more solute and have it dissolve. So let's say that our solubility was 90 grams of solute for every 100 grams of water. An unsaturated solution might have 45 grams of solute in 100 grams of water. Or it might have 90 grams of solute in 200 grams of water. These are both examples of an unsaturated solution. Does everybody see that? We're underneath the maximum amount of solute that can be added and still dissolve. So we good on unsaturated? Okay. Saturated means that you already have the maximum amount of solute that can be dissolved in that volume of solvent. You're going to have undissolved solute at the bottom of your container. And that solute is going to be kind of going back and forth between dissolving and falling out of solution. Dissolving, falling out of solution. So if we go with our example of saying 90 grams of solute and 100 grams of water, if that's our solubility, if I had 100 grams of solute and 100 grams of water, or if I had even 95 grams of solute and 100 grams of water, those would be saturated solutions. They have more solute than is actually soluble in your solvent. Is that clear? So let's take a second and identify each of these as saturated or unsaturated. A, salt disappears when you put it into water. Is that saturated solution or unsaturated? This one is unsaturated. Unsaturated means that you can add your solute and it's going to disappear. It's going to dissolve. So that means lower than the solubility. With B, though, sugar added to a cup of water does not disappear, but sits at the bottom of the cup. That's a saturated solution. So if there's questions, let me know. Okay. Yeah, there's a lot of terms in this chapter. So getting them all down, a little bit of a challenge. Yeah, it's totally fine. Let's do a solubility one. Now, I told you that temperature has an effect, so we're being pretty specific in this question. At 40 degrees Celsius, the solubility of potassium bromide is 80 grams for every 100 grams of water. Identify the solutions as either saturated or unsaturated and explain. You don't have to really do the explain part. But I'll give you 2 minutes to read each of these conditions for A, B, and C and identify whether the solution is saturated or unsaturated. Okay, is anybody else stuck or a little confused? Okay. Then let's work on it together. So in A, we've got 25 grams of potassium bromide added to 50 grams of water. This is our solution. Our maximum solubility is 80 grams of potassium bromide in 100 grams of water. So have we dissolved less or more than 80 grams? It's not a trick question. It's less than 80 grams. Okay. Oh, I'm sorry. This is 50 grams. See, I'm reading it wrong. So if we were to have the same denominator, it would be like saying 50 grams in 100 grams of water. Either way, it's still below the solubility. If we're below the solubility, then that means that you are unsaturated. If you've dissolved more than 80 grams of potassium bromide for every 100 grams of water, then you're saturated. So for B, we've got 30 grams of potassium bromide added to 30 grams of water. Do you think that's saturated or unsaturated? Oh, I'm sorry, I see a question. Oh, yeah, okay. I just addressed that. So for B, we've got 30 grams and 30 grams. Saturated or unsaturated? Yeah, it's going to be saturated. For C, we've got 80 grams added to 200 grams of water. Saturated or unsaturated? Unsaturated. So does that help a bit more? Does it make more sense than it did before? It's exactly like proportions. You're comparing the two. All right. So that's kind of the number type stuff on solubility. Now we're going to talk about temperature and pressure. First, temperature. When it comes to solubility, we can talk about gases and we can talk about solids. The solubility of gases decreases in liquid as the temperature of the liquid increases. So if you think about a soda, right? If you open it up, you take a sip, and it's straight from the fridge, you leave it out on the counter because your phone rings or something happens, you go do whatever, you come back like, oh, my soda. And you take a sip and you're like, this is trash. Because it's not carbonated anymore. That's because the soda has warmed up, and that carbon dioxide that was dissolved in the soda is no longer there. It's no longer soluble. Does that concept make sense? Because it's a little bit of the opposite of solids, which is kind of what we think about the most. So that's for gases. In the YouTube video, I have a separate slide on solids, but I didn't do that here. So the solubility of solids in general increases as the temperature increases. So if you think about, I don't know if people do this anymore, but I know if I got sick and my throat was hurting, my mom, my grandma would be like, gargle some salt water. I don't know if people tell you to do that anymore, but it does help. If you get cold tap water and throw some salt in there, it's just going to be sad. And you're going to have crystals of salt, and you're just going to be angry. But if you warm that water up a little bit, and then you put the salt in there, it'll dissolve a lot easier and quicker. That's because the solubility of that solid increases with the temperature increase of the water. The same thing goes for if you're boiling pasta. If you add that salt to cold water before you started to heat it up, it's not going to dissolve very well at first. But as the water heats up, then you'll notice the salt starting to disappear. So that's the two concepts on the effect of temperature on solubility. Gases decrease in solubility. Solids increase in solubility as the temperature of the solution increases. So remember that concept. The other thing we can talk about is pressure. And we're going to go back to our soda example. When you open a can of soda, or LaCroix, that's my favorite. I don't really drink soda. I'm too bougie and I like my teeth. But I'll drink some LaCroix all day long. Maybe I'm just old. But when you open that can, there's always a space. It's not filled all the way up to the top with liquid. There's a little bit of an air gap between the liquid and the top of the can. In that space, there's gas molecules. So we said that there's carbon dioxide dissolved in the soda. Some of it is not in the liquid. It's hanging out above. And in that space, before you open the can, it's a fairly high concentration of carbon dioxide. And in the liquid, there's also a good concentration. Once you open that can, you release all that gas. And as the can sits, it gets warmer. It's also got a venue for all those gas molecules to leave. So the pressure of carbon dioxide above the liquid decreases. Henry's law says that the solubility of a gas in a liquid is directly related to the pressure of that gas above the liquid. So before you open the can, the carbon dioxide is very soluble because you have a good amount of that gas hanging out above the liquid. You open the can, all of that gas is gone. So the carbon dioxide in the soda is like, hey, I want to be free too. I'm going to join my friends. And it liberates itself. So now you've got a lower concentration of gas above the liquid, and that also means a lower concentration in the liquid, and your soda is fitting to be flat. Does that concept make sense? It's a little, when you think about the soda can, at least for me, it helps put it in context. But let me know if that's clear, because it's just very conceptual, very heady, abstract. If you think of another example, or if you see like a YouTube video or something on this that you find to be very helpful, please share it with me, because I'm always looking for things like that to be relatable, to talk about conceptual, abstract things. Okay, yeah. Sometimes it takes a second to like let it permeate your brain. So we talked about temperature, we talked about pressure. Pressure, and I just want to reiterate, we're only talking about gases in liquids. That's what Henry's law applies to. Gases only. Okay. To talk about solubility of compounds, so solids, we have to talk about solubility rules. So some things will dissolve in water, some things won't. When it comes to ionic compounds, some compounds will dissolve in water and some things contain insoluble ions. When it comes to an insoluble ionic compound, the bonds between the ions in that compound are too strong for the water molecule to be able to break them up. That compound would prefer to stay together than break up. The solubility rules that you see in the table are the rules that we can use to predict whether an ionic compound would be expected to dissolve in water. I will give you these rules for the exam, so you do not need to memorize them, but you will need to know how to use them. It's kind of like those logic puzzles. So I'll walk you through an example. Let's say that we had lithium chloride, and we needed to figure out whether it would be soluble or insoluble. You look at the table. An ionic compound is soluble in water if it contains one of the following. We see the lithium ion. Okay, well, we have that in ours. So that means that this is probably soluble. We also see that ionic compounds with the chloride ion are usually soluble too. So our prediction is that lithium chloride would be soluble. Let's say we had lead-2 sulfate. We look at the positive ions. Okay, well, I don't see lead there. So let's keep looking. I see sulfate on the table. Sulfates are usually soluble except when combined with lead-2 plus. Well, I have lead-2 plus sulfate. So that means that this is likely insoluble. That's the kind of logic you will need to use when it comes to determining whether an ionic compound is soluble or not. Does that make sense? I have some examples for us to try, but does it make sense, kind of the expectation of how to use the chart? Okay. And again, for everybody who's not chiming in, hope you're still with me. Feel free to say, hey, I'm stuck. Don't feel bad because other people are saying yes. You paying tuition too. So if it's, I don't get that, or can you run that back? That's totally fine. That's what I'm here for. Go for it. Sure. I'll give you another example. Then we'll go and do some more. Let's choose another color. I'm feeling purple today. Let's do cadmium sulfate. Cadmium, we don't see in the list of positive ions. So we're still not sure whether this is going to be soluble or not. For the negative ions, well, we've got sulfate. And sulfates are usually soluble except for these exceptions here. Barium, lead 2, calcium, strontium, mercury 1. We don't see cadmium on there. And since sulfates are usually soluble, we're going to say that cadmium sulfate is likely soluble. Does that example help, Jordan? You're fine. You're fine. Let's do some practice. Because I think practice is what helps. So I will give you a few minutes to work on these two questions. And I gave you the solubility rules. You're supposed to figure out which one is soluble in water. I'll give you 2 minutes and then I'll check back in. Alrighty. So I see y'all putting in your answers. That's good. Let's go through it. We're looking for compounds that are soluble in water. A, B, and C are all sulfates. So we're going to be looking at that rule for the sulfate ion. Sulfates are usually soluble except when they have barium, lead 2, calcium, strontium, mercury 1. Well, barium and lead 2, not soluble in water. So it's got to be A for the first one. The second one, again, we're looking for the compound or compounds that are soluble in water. We don't see anything about CO3 on here, that negative ion. So we have to look at the positive ions list. Anything that has the NH4 plus ion, we're going to say is soluble. Everything else is suspect. So you should get A for both of them. Questions on that? It just takes practice. Yeah, go for it. So what it's saying is that for all of them, so if you saw that, or that, they're all insoluble. Okay? You're welcome. Other questions? All right. Here's another one. So we didn't talk specifically about double replacement reactions. That's in the YouTube video. But I wanted to do this one with you so that you get a little bit of a taste of it. So in a double replacement reaction, you're swapping ions. So you have silver nitrate and potassium carbonate. You're mixing these two. And what happens is, if we write out these are the ions that are going to be in solution. Once they're in solution, they have the opportunity to swap partners. So we can form two new compounds. If we form these two new compounds, we have to see whether or not one of these is going to be soluble or insoluble. So the question is asking about what are the products, but I'm using it to kind of talk about solubility too. So for the double replacement reaction, we would make these two things, potassium nitrate, and we'd make silver carbonate. But what I want you to do is figure out whether one or both of these is soluble. So figure out, is KNO3 soluble and is silver carbonate soluble? You can put your answers in the chat. So for time's sake, I'll start going over it. The first compound, we've got potassium and we've got nitrate. Things with potassium, usually soluble. Things with nitrates, usually soluble. So it's pretty safe to predict that's going to be soluble. Silver carbonate. We don't see anything about silver being on the list of positive ions that are usually soluble. And we don't see carbonate as part of the list of negative ions that are usually soluble. Since neither one of these things shows up, then we can predict that will likely be insoluble in water. Yes, go for it. No. So what you see here is the negative ions that are usually soluble are chloride, bromide, and iodide, except when they're combined with the positive ion of silver, lead 2+, or mercury 1. So these that are listed here are insoluble. And it's the same for the sulfates. Okay. Right. Right. You're welcome. So like I said, this will take practice. And I will make a note to myself to put some practice up on Blackboard for solubility. This is a good time for a break because we're switching from kind of more concept heavy stuff to doing a little bit of math with concentrations. So we'll take 5 minutes, shake your brain out, do what you got to do, and then we'll get back to it. So it's about to be 12:39. Let's just say 12:45. So take about a 5-minute break, and I'll see you back at 12:45. All right, everybody. No more break. We're back. And we're going to get started with solution concentrations and reactions. When we're talking about the concentrations of a solution, it's always going to be about the amount of solute versus the amount of the solution as a whole. You can express the amount of solute as grams, milliliters, or moles, and the amount of solution, grams, milliliters, or liters. We're going to talk about a few different ways that we can calculate concentration. The first is mass percent. So we're looking at the mass of the solute and the mass of the solution. Note that the mass of the solution is equal to the mass of the solute plus the mass of the solvent. And you multiply that by 100%. You can also use the mass percent as a conversion factor. And we'll address that in a little bit. This is a learning check for calculating mass percent, which I'll write again how you do that. So the mass percent is the mass of the solute over the mass of the solution. And the mass of the solution is equal to the mass of the solute plus the mass of the solvent. And take a second and figure out what the mass percent is. Hopefully everybody's still with me. And you can put your answer in the chat. I'll start filling it in. So the solute, we have 15 grams. The mass of the solution is going to be the sum of the solute plus the solvent, which is water, and we multiply that by 100%. Before you do the 100%, make sure that you do this addition in the bottom first so that you get the right number of sig figs. So it should be C. Questions about that? There are a couple of other ways that we can calculate concentration that are very similar in concept. We've got volume percent, which is where we have the solute as a liquid and the solvent is a liquid. So the volume of the solute goes on top. The volume of the whole solution goes on the bottom. And then you multiply by 100%. Remember that the solution means solute plus solvent. Those volumes add. Again, we're going to talk about these percentages as conversion factors in just a second. I just want to introduce the other type. We also have mass by volume percent. So you have the mass of the solute and the volume of the solution. In this case, the volume of the solution is the volume of the solvent. We're assuming that the mass of the solute that we're adding is so small it's not going to change the volume. So that's a key difference between volume percent and mass percent. But we're going to do some problems in a second. I want to first address the conversion factors. So I'm going to do A for you. When we're looking at these percentages are always out of 100. So when we think about grades, if you got an 85, that's 85%. 85 out of 100 points, right? It's the same thing with these percentages. What that 5.75% means is a fraction. But we need to assign what this really means. With volume to volume, we're talking about 5.75 milliliters of ethanol and 100 milliliters of solution. And that comes from knowing what volume by volume percent means. That's a conversion factor. We can use it to figure out how much ethanol we need to add to make, say, 150 milliliters of solution. Or if we know that we have 300 milliliters of solution, we can figure out how much of that is ethanol. And for conversion factors, if we can write one, the second conversion factor is just the reciprocal. So try your hand at part B. You don't have to write it in the chat because it's not the easiest thing to do. But try it, see if you can wrap your brain around it, and then I'll write it out. I'll give you a couple of minutes. Alrighty. Bless your heart for writing it in the chat, because that takes some time. Probably more time to write it in the chat than it does in your notebook. So for B, we've got 4.8% mass by volume HCl. We know that 4.8% is 4.8 over 100. But now we need to assign what those numbers actually mean. For the mass, we're always going to go with grams. And the solute is always going to be listed here, HCl. We're assuming that we're in water here. For volume, we're going to go with milliliters because that's typically what it's in. and that's the volume of the solution. That's one of the conversion factors. The second one is the reciprocal. If you weren't able to get it, that's okay, but does that concept make sense? All right. Let's move on. Here's some mass to volume and volume to volume practice. So I will write out what those are, and I want you to give these a try. So you've got mass by volume and volume by volume. I abbreviated volume as V or VOL. So I'll give you a couple of minutes to try these out. Again, we didn't spend a whole lot of time on this, so it's okay if you don't get to an answer or you're like, don't really know how to solve this one. That's totally fine. But I wanted to give you some examples. These are some sample problems that you might see on an exam, just to give you an idea of the types of questions you're going to encounter. I'll check back in another 2 minutes. So in the interest of time, I'm going to start setting this one up. And I realized I wasn't recording when I introduced this second learning check question. But hopefully it'll make sense once I go over the problem. So we're trying to figure out how many grams of aluminum chloride you need to prepare 125 milliliters of a 0.150 molar solution. The first tip, always make sure your volumes are in liters. And that's what we did here. To solve the problem, you have to take your molarity, multiply it by the volume to get the number of moles you need to make the solution. You can't measure moles, but you can measure mass in grams. So you take your moles and multiply by the molar mass to get grams. To fill in the numbers, you're going to take your volume of 0.125 liters and multiply by your molarity, which is again moles per liter. That tells you how many moles of aluminum chloride you need to make this solution. Then you have to calculate the molar mass of aluminum chloride. So you look at the periodic table, you find aluminum, you find chlorine. The chlorine you need to multiply by 3. You add all that together. You should get something in the ballpark of 133 grams per mole. Now we take that and multiply the number of moles we have. With my calculator, I got 2.51 grams, but that's pretty close. Close enough to get you in the ballpark. So those are some samples of the types of problems you'll have to do for the exam. Yes. Yes. Volume by volume. You're welcome. So that's where we're going to stop for now. We'll pick up with this next week. We have to talk about dilutions and calculations for those. And then we'll also talk about properties of solutions to wrap up Chapter 9. And then we'll do a few sections from Chapter 11. So I'm going to skip forward to my reminders. No office hours this week. Don't forget. So if you need something from me, you need to send it in a course message or something and get it to me ASAP so that I can get to you by 5, which I teach another class right after this. Once 5 o'clock hits, Dr. Hefner is going to go to rest. Mama Hefner is going to emerge, and I'm going to be with my family. We're having a baby, so that's a little bit important. Your Mastering Chemistry assignment is actually a combined assignment for chapters 9 and 11. Typically, we teach these chapters together, so you don't have an assignment due until after we cover both of these chapters. So that will be on November 15th. You can, however, get started on the homework with the stuff that we've covered already, and you can bring your questions to class or to office hours next week. No chapter check-in this week. We're done with chapter check-ins. It's the end of the semester. I know y'all got a lot to do. Your next exam will be available Wednesday, November 18th through Friday, November 20th, and it will simply be on what we cover in Chapter 9 and Chapter 11. You have a final exam, and that is slated for Tuesday, December 8th, 11 to 1 p.m. So it will still be online, Respondus lockdown, multiple choice, but there's no several day window. It's this specific time. So if you work, make sure that you have this time off. You have to start the exam within this window. I'm not going to say you have to finish it in this window, but once you start it, you'll have 2 hours to complete it. So make sure that you can start your exam on Tuesday, December 8th, between 11 a.m. and 1 p.m. Next week, we'll talk about whether or not you guys want to have some kind of a review or anything like that, or if we just want to have some special office hours, because there's a couple of weeks in between the end of classes and final exams. So we'll talk about that in the coming classes. If you have any questions for me, this is a good time to do it, or you can send me a course message. Otherwise, you're free to go.